Welcome in this session. Thank you for coming. So, in this session we are going to speak about Reactive and what it means for you today, what's the impact on your applications, and how you can use Reactive and why Reactive can be a good thing for your system. So my name is Clément Escoffier, I'm Chief Architect at Red Hat, and I'm orchestrate everything related to Reactive, so that's why I'm here.
And I am Ozan Günalp, I'm architect at Defray.com. It's a website for insurance comparison in France.
So in Defray.com, so it's an insurance comparator, and there are lots of Reactive, or a lot of issues that Reactive can fix, and we are going to see that. So there is something about Reactive. In the last few years, everything became suddenly Reactive. So there is many things that have been associated with Reactive, and even to make things even more confusing, there is a lot of concepts around Reactive. So the first question we should ask is that the same Reactive or is that several Reactive? So these words are more or less, if you go on Google and you search for Reactive, the top word you will find are this one. But there is a path. This one. So the first thing is Reactive comes from the need to build responsive system. So responsive system means answering to requests in a timely fashion even when under fluctuating load or facing failures. This concept of responsive has infused a Reactive manifesto that has been written 5 years ago, which defined Reactive systems, an architectural style to build responsive system. Reactive systems are based on the concept of message, resilience and elasticity, but the core essence of Reactive systems is the need of asynchrony. However, as soon as you touch asynchronous code, you want to kill yourself. Seriously, we will see that. So we need a way to write asynchronous code, and there's many things. You can use callback, but you should not, except if you are a JavaScript developer, or you can use actors, fibers, or events, or even spreadsheets. Do we have project manager here? Or people using Excel or something like that?
No, all developers? No.
Okay, one. This guy over there is probably the best Reactive programmer we have in the room. He doesn't know it yet. But everything you do in Excel is actually Reactive programming. Do we have a few Java developers here? Oh yeah, okay. So I have a very bad news for you at the end of this talk. Anyway, let's go back. So Reactive programming is a way to tame the asynchronous beast by providing an API to build asynchronous software. This API is based on the concept of stream, but as soon as you have a data stream, you have an issue if you have a fast producer and a slow consumer, because you are going to overload your consumer. So for this we need Reactive streams, which is a specification to implement a non-blocking back pressure protocol. So here we are really in the data flow world. However, this is a very low API. It has 4 interfaces and you should not try to implement them by yourself. There is a TCK that is going to be your nightmare for months if you do that. So fortunately, we have Reactive extensions, which is based, since V2, on Reactive streams. So you don't really have to understand Reactive streams, it will just provide everything you need to build on top of Reactive streams. So here we have two things, Reactive Java 2 and Reactor. So Reactor is not strictly speaking Reactive extension, but because they have more than 50% of the code in common, we can say that they are very similar. So let's continue. I didn't define what Reactive means. And if we take the Oxford Dictionary, we can check out at this address here, Reactive is defined as showing a response to a stimulus. This is vague enough, but if we try to map this definition to software, then we can say that a Reactive software is some code reacting to stimuli such as user inputs, messages, and failures. And here you can say, well, come on. Isn't that the nature of software to obey to operating system, to do things on hardware interruptions and to follow the user inputs? And you're absolutely right. Every software we build since the beginning of software is in some sense reactive. However, the world has completely changed with the cloud, IoT, data streams, and so on. So this needs to be changed a little bit. And what changed is the second part of this definition, this one, acting in response to a situation rather than creating and controlling it. Because this is the end of the flow control. When you develop your Java applications, you do the first instructions and next instructions and third instruction and so on in sequence, right? It's easy to debug and so on. Yeah, but here is reactive. You don't define what's next. What's next is defined by the next message, user input, or whatever you will receive. So basically, it's just a comeback of asynchrony. We have ignored asynchrony since the 80s and it's going to beat us. So we need to find a way to do that. Thank you.
Oh yeah.
This is reactive.
So in the reactive landscape, we have the reactive systems that have the asynchrony, reactive programming that has the asynchronous nature, and we have the reactive streams that helps us to build up this asynchrony with data flows and non-blocking back pressure. So Clement was talking about the applications and how the reactives are introduced to the applications, but in the beginning of time, we have our application, we have our users, and usually a simple application has data to access. So this is my basic application that we've been writing all the time, right? So then we said, okay, we'll maybe introduce we'll use other web services. So maybe we had the monolith and we will split up our monolith to different services and we will use that services. Let's say it's Google OCR or it's a new service that they've introduced. Or in our case, in Lefray, we have like 60 to 70 web services that we call each every time for an insurance code. So that is introduced as a different component of our system. Another component is the APIs that we produce, that we propose to other systems. So users are not the only users of the system. Other systems try to access our application. Of course, we live in an app world, so maybe we push some of notifications to our users, right? So it's not only users coming to our website, we are pushing data to our users also. And of course, we are good players in web. We are trying to monitoring our application. We are sending logs, sending data of our status of our application, the health checks. So all this live in a distributed world. So web services that we are calling are in remote machines. The databases are remote machines. Other software, third-party software that are calling our application are in a remote system. All this is subject to distributed communication. And as all we know, distributed systems fail. So if our application will access to our database, there will be latency that will affect our users in first hand, but the other system, the third-party systems that are trying to access our application, of course, web services that our app are using will fail. In our case, I can assure that not in one point of time not all the web services are working as they are supposed to. Of course, the interactions with our application are different from the user and from third-party services. Users have a pattern of using our website, but third-party apps that are using the APIs can have different workloads. So all this means that distributed computing will fact that our application will fail and are subject to all these different conditions. So our application will degrade on time and it should react on all of these. Our response to that, as someone was saying, the reactive manifesto, right? So the guys who wrote the Reactive Manifesto started from the fact that we need that responsiveness in our applications. How do we do? The responsiveness is linked to the fact that we want to scale. So we should be elastic in our scaling of different workloads. But our application should be resilient also, because distributed systems fail, different applications fail, different components fail. So we should be responsive to the failure also. And all these are, in essence, enabled by the message-driven architecture that we'll use in our application. Well, they've written message-driven, but what they are really wanted to say is the asynchronous message passing. So what's that? Asynchronous message passing is the fact that when your two components of a system are trying to communicate, one, instead of telling to a direct line, okay, I will call you in that line, it sends a message to a third party, to a message backbone, which it addresses with a virtual address. It's not an IP address, but it's an identifier in our message system. And the subscribers are listening on those addresses. So there you go, you have the decoupling between the consumers and the publishers. And then I can go ahead and scale my publishers, scale my consumers in a number of, so I can scale it elastically. And because my backbone is there and the messages are transferred by it, I'm not subject to the failures of the consumers. And the important thing is my producers are not blocking on the fact that my consumers are listening or not. And of course, my message backbone can have different features as to buffer the messages if the consumers are not listening, if there's no publishing on the sender side, etc. At first hand, the message backbone seems like a single point of failure, but of course we know how to do that. So there you go, our reactive applications becomes like that. We have messages everywhere. My application is just handling different messages, receiving messages, sending other messages, etc. So this is a reactive hell. So it's a Kraken that sends messages. It only reacts to different kinds of messages, right? Different kinds of events.
One thing about this is, if you follow a thread-based approach, as most of you are probably doing today, every single request will be attached, will have an affinity with a thread, and the thread will handle the complete request. The issue here is, if you do that, according to the number of messages you are going to have, you are limiting your concurrency by the number of threads you have. So there is many things that are hidden behind threads, and the cost of threads is erroneous. It's very expensive, especially in containers. So you need to really understand that thread-based systems cannot really make the next generation. It doesn't really fit the new model, so we need something a little bit different. And with threads come race condition, deadlock, live lock, volatile. Who knows what volatiles really means? Oh, we have 3 people here. But I have good news for you. They change a little bit the semantic between every version of the JVM. So maybe what you know about has changed recently. So it can become very messy, and you don't want this. So one of the things we can do to that is to completely redefine how we execute software. And in a thread-based model, if you have 3 requests to handle, you will do the first one, then the second one, then the third one. Well, that's the ideal world. In the real world, you are going to do the first one, and then, well, you need to call a service. It's a remote service. And because you are using a thread-based model, you are using blocking I/O. So your thread is blocked, waiting for a response. Block doesn't mean that it does not cost 0. It costs things for your applications. CPU cycle for the switch, memory because the thread is still there, and so on. So every time you do any blocking I/O, you are going to be stuck in this blocking state and not making any progress. So again, as I said, if you want to handle concurrent requests, you need to scale the number of threads. More thread you have, more memory you use. More thread you have, more CPU you are going to use to do the CPU switch. So basically, you are paying, because that's what you pay in the cloud, or inside your container, you are paying for nothing, waiting. Well, I know that in Istanbul, you love waiting in the traffic jams. You maybe experienced that yesterday, but your application doesn't really want that. So the asynchronous execution model is a little bit different. As soon as a task cannot make progress, it relies on non-blocking I/O. So the thread is released immediately and can be reused to handle another task. So instead of having task A, B, C, we start A, cannot make progress. So we start B, cannot make progress. We start C, and so on. And when we get the first response for A, we restart the execution of the task A, and so on. So if we follow this model, we actually even have some spare time over there, that's the yellowish block. So we are saving time, money, and we are working in an efficient manner. So for this we need three things. We need an asynchronous programming model, we need non-blocking I/O, and we need a task-based concurrency model. So let's start with the model. So the easiest way to write asynchronous software is to use callbacks. So I picked this example from Vert.x. So you create an HTTP server and it's reactive. So every time you get a request, this handler is called and you reply to it. Reactive greetings and so on and so on and so on. So we really see the reactive pattern here. And then we have the listen part where we are actually starting the HTTP server, and there is many things happening at the operating system level when you do that, because maybe the port is already used. It happened to me often. So it takes time, and the second lambda here is going to tell you whether or not the operation has succeeded or failed when it has completed. That looks nice, right? 2 callbacks and we're done. So let's have a look. This is how we interact with the database. Things start to become messy. Because you first get a connection, this can fail, so you need to do failure handling. Oh, and you cannot throw exceptions, because the thread is reused by many things, so you don't throw exception, you need to propagate exception. Then once you have the connection, you need to do the query. This will return again an asynchronous result, because the time we establish a connection with the database and so on, execute the query, and so on. And then you get your result, you need to iterate over that, and don't forget to close the connection, because if you don't close the connection, it cannot be released and not recycled in the pool, and so on. So, and this is just for one very simple select star from products. Imagine if we do that for the complete system. Well, we have a callback hell, and you don't want this. So, to do that, it's what reactive programming can become very, very handy to what I call change the asynchronous beast. So, in a reactive programming world, everything you are manipulated as streams of data. So you have operators to create streams, you have operators to combine and transform streams, and there is this subscription step. So streams are very, very lazy by default. So for me, they are a little bit like French. I'm French, I can say that. If you don't say to the French people that you actually need the report, nothing is going to happen. Yeah, later, next time, PTO, strike, or stuff like that. So, and for stream is the same thing. You absolutely need to subscribe or nothing is going to happen. And you can be sure that the first mistake you will do when you use reactive programming for the first time is forget to subscribe. So we'll start your system and nothing is going to happen. It happened to everyone. It even happened to me. Actually, if you're interested to know more about reactive programming, there is a workshop this afternoon about exactly this. And I'm sure you are going to forget to subscribe.
So yeah, well, we have Java streams also. We are, beginning from the Java 8, we have streams also, but the streams in Java 8 are streams of data. We have a collection of items, we are streaming on it, and what we are trying to do is to describe how we are transforming the data, where we are writing a data flow. In reactive streams, what we are trying to do is to define declaratively the transformation of events. So what is an event? It can happen several times. It can end with a completion, with a success, or it can end with an error. So an event in reactive streams is the event on next can happen several times. Then it can end with an error, or it can complete with a success. Then on top of the events, stream of events, we are adding the operators. So reactive streams are combining the best parts of observer pattern that Clement was saying, the subscriber pattern. Then we can iterate on events, not the data itself, and then we can apply functions on it declaratively. So there we go. We have a reactive stream, and then we have a map on top of it that in which we are transforming the data. Then we have the flat map.
So flat map is a bad name because it's actually map and flat. So the first thing you need to understand about operators is that applying an operator to a stream is 90% of the case returning a stream. So for example, for map, if you get 1, then we will return 2. But if you get the stream of 1, 2, 3, you are returning a stream of 2, 3, 4. Okay. So flat map is based on this idea, but it should be named map and flat. But as nobody can pronounce it, they switch it. I'm pretty sure that's the only reason. So the first thing we will do is a map. But instead of mapping that to a single element, they are mapping that to a stream of elements. So here, for example, I get 1 and I create a stream of duplicating the elements, so 1 and 1. So if I just do map with this, that will be a stream of stream. The first stream inside my stream is 1, 1, then 2, 2, and then 3, 3. But I want a flat stream. Here is a flat part. So it flattens our result, all the streams we have returned, to make it them in one stream. So here the order is respected and enforced. But it's actually not the case in reality, and depending on the flavor you use in terms of flat map, because that's a simple form, but there are many. This may not be in the right order. And it's okay. Streams are asynchronous in the sense that you don't know when the signals or the values are going to be emitted. So it's fine if you know order is better actually.
Yeah. So there are different kinds of streams, of course. In stream of Java 8, all the items are ordered, but then and bounded. You have a collection on top of we are describing data flows. But in reactive streams, that can be unbounded. So we can have events on a stream that cannot finish and be unbounded. Then we can have data or errors transformed to the stream. A stream can have single events or multiple events, as we are telling, and maybe we are just an event is just a completion of a task that will be executed on future. So maybe we are not really expecting a data at the end of it. So that's why we have the completables. The code that we were trying to write in Vert.x with callbacks, now we can write using reactive streams. So instead of getting a connection, I am telling that I have an intention of getting a connection that will return me a single of connection. Then I'm using that lovely flat map publisher method. Greatly named, which will end up having a flat map on connections. For each connection that I'm getting, I will make a query, gather the responses, and of course handle the case that if I should at the end of it close the connection. And at the end of it, I have a flowable a reactive stream of rows that I gathered from database. Then I make the transformation with the map. Now I have a stream of products of my business model, and then I should until now I did nothing. I should subscribe on it to be able to execute on it. And it all goes well if I have a stream of events that never stops and it goes on constant. Well, how to say, a traffic of constant events. But it is usually not the case. Maybe the producers that are sending the events are too fast or usually too fast for us to consume the events. So that causes a problem in our stream, because now we have a list of events that we cannot consume in the same pace. That's why we have the back pressure. Well, we have the exactly non-blocking back pressure. So we can always use the fact that, okay, if I cannot really consume, I can block on it and say that, okay, I will put it on a queue. But reactive streams handle the back pressure in a non-blocking fashion, is that the publishers or subscribers do not to block and queue the messages. So we are transferring the responsibility of handling the back pressure to the publisher side. That's to say that we are asking for an event. If the publisher has an event, they will push on it, they will push the data, and we can consume it. If I'm not able to consume the data, I won't demand it, and the publisher won't send it to me. And it will handle the event, the fact that it has a data by itself, using different strategies. Let's say maybe it will drop the message, maybe it will put it in a queue, maybe it will send an error. Do you want to add something?
No, that was good. Yeah, okay. So let's talk a little bit about Vert.x. So I'm a Vert.x core committer, so I can answer almost all your questions about Vert.x, but here is a very high overview about Vert.x. So the first thing to understand is that Vert.x is a toolkit. It's a jar that you can embed in any Java application. The only thing you need is a JVM. So there is absolutely no problem to embed a Vert.x in a Spring Boot application, in a Java EE application, or even, and we will see, in a Quarkus application. So Vert.x has been designed since the first line of code 7 years ago with Reactive in mind. So it's not something that we have added as an afterthought. It's something that we know since the beginning is what we want and why we want to do it that way. Because we are all different, we are not proposing one asynchronous development model, but several ones. So we have seen callbacks, we have things with Java 2, but we have other things. We have coroutines with Quasar, and for Kotlin, we have futures, we have many other things. And it's even increasing for Vert.x 4, that should be released, let's say fall, or something like that. We have a task-based concurrency model based on the concept of event loops. So basically your Vert.x application is single-threaded. It's not necessarily true, it's 2 event loops per CPU core, but for you as a users, it's single-threaded. So if you are not users, it's exactly the same model. It's polyglot, so it's not only Java. It has a cluster event bus, and it's used today in production, mainly in fintech, but not only in fintech, for microservice, web apps, IoT, API gateway, high-volume event processing, and so on. And it's rising at the moment. So why Vert.x is interesting here is because Vert.x has been designed to build reactive systems, understand reactive streams, and has its own also own back pressure protocol, but we understand reactive streams, and you can use reactive programming with that. So you don't need to say, oh, which part of reactive is important for me? You just use Vert.x and you have all of them. So if we would take our application and we want to make it Vert.x, that's probably a lot of work, right? Oh no, that's going to be lots of rewrite, and we need transaction, and oh no, and messages and so on. Exactly, this application is 100 line of code, including comments. And I'm writing a lot of comments. I love comments. So the first thing we need to do is when you get a request, HTTP request, we already see that code. We are going to call this add method. And the routing context is basically your request, and you can reply to it. You connect to the database using database.insert, which returns a single of connection, a single result with the updated product, with the ID, auto-generated ID. So behind this database.insert is going to connect to the database, do the SQL magics, get the thing back, extract the key, and this is different for every database. I love this. SQL, you're my lovely standard. And, well, extend my object and return that. And when it's done, so I subscribe, if it's successful, then I just say accepted, tier 1, and then if it failed, I just return a 500. It's what RC column fail is doing. When I want to list all my products, the first thing I will do is use chunked request. So chunked request is not something new. It's something coming from HTTP 1.1. So it's very, very old now. We're speaking about HTTP 3 these days. So chunk request means that you are going to write to the request even if you don't have the complete response computed on your side. It matters a lot under concurrency. Because if every time you try to accumulate the complete objects inside your memory and then write it down, it works if you have 5 users. It doesn't work if you have 10,000 of users, because then you have 10,000 blob to store in your memory, and you have a memory hog. And you don't want this. So here, as soon as you get a result from the database, you write it immediately. So how it works, then we have database.retrieve that return a flowable of product, so it's already mapped into purgers, and then in the subscription, for every for every product, we are going to write it directly in the response, but we don't close the response yet. We need to finish to iterate. If we have a failure, we just fail, and when we have the end of stream signal, we just close or end the response. Here, don't use close. Close is abruptly closing the connection and is really sending the last things. So in our application, for every product we retrieve from the database, we need to call another service. Oh, so we need a way to do asynchronous operation composition. It's actually very easy here. We retrieve all my product from the database. Again, it's a stream of product. Then for each one, I'm going to call flatmap single using a web client, which is an HTTP client for Vert.x. And this is how you call an HTTP service in Vert.x. And for each result, because it's a flat map, it will go back in a stream, so a stream of product with the price is set, and do the very same thing. However, here I'm using a web HTTP client, so using an URL. And what we say about reactive system, we should not use URL, we should use messages. The same code with messages using the Vert.x event bus. So it's very simple. You use Vert.x event bus or instead of the web client, and the rest of the code is almost unchanged. And instead of calling an URL, you are calling an address, so you don't care if there is one or more pricer services here. It will just dispatch using a round robin. Simple. So we really have location transparency and things like that. Finally, recently, and I'm sure we can do a test here, how many push notifications you got on your phone since the beginning of this session? I got at least 5 or 6. So if we are all there, it's probably 1,000, something like that. So we completely change the way we consume data. Users don't want to pull the data anymore, they want the data to come to them. So we need a way to do that. And the way we use in Vert.x to do that is named SockJS. So SockJS is a weird beast in the JavaScript world because it's a JavaScript library that is more than 6 months old and still alive, which is surprising, but yeah. And it's going to negotiate the exchange, the protocol used for the exchange between your browser or mobile and so on and your applications. So by default you will use WebSockets. That's great, but there is some browsers that doesn't use WebSockets or doesn't support them. So we will fall back to SSE and so on until it goes to long polling and even iframe with Ajax and stuff like that. So, but our application interacts with SockJS. SockJS brings this event bus to your clients. So basically, you just use Vert.x.eventBus.publish saying that you get a new product. And the client will have connected to SockJS, will receive this, and on the client side you say, oh, when I have a message on products, then I know that it's a new message that has been sent on the, that has been written in a database, and I can react immediately. Is that hard? If you take the other example of how you use WebSockets and stuff like that and degrade correctly, here it's one line of code, a single line of code. The last point where what's interesting is about concurrency. So I use the term concurrency and not parallel, because these are two different things. Parallel means doing two things at the same time, exactly at the same time. So on my machine I have 8 CPU cores, so I can do 8 things at the same time. Makes sense? 1 per CPU core. Concurrent doesn't mean that. Concurrent means I can get plenty of requests, and I'm going to process them in a timely fashion, but yeah, it's not only 8. It would be a nightmare if it would be only 8 requests a second or requests at the same time. With Vert.x, with not this application but something very similar, on a Raspberry Pi Model B, you can handle 10,000 requests per second without tuning. If you tune it, you can go up, but yeah, with a single thread actually. So it's very concurrency. That means that I have 2 calls to do, 2 asynchronous calls to do. I need to call the audit system, and I need to call the pricer. They are not related. So it's fine, because as they are not related, I can fire both, and when both are done, join them and continue. When I say join, it's not thread.join. Thread.join is terrible, it's blocking, don't do that. Here you just use zip. Yeah, it's a weird thing because of the zipper. Yeah, okay. Sometimes names. So you just say, okay, I want to be notified when my price operation and my audit operation are completed or failed. And I continue. And so on. It's how you achieve concurrency, asynchronous concurrency with Vert.x and Heroic Java 2. And again, if you want more details, there is a workshop tonight. So let's switch to a demo. Is that readable? Yeah. So, oops, that's not what I wanted to do. Okay. I think I just closed my database. No, my database is still there. Let's see. So the application will be structured like that. So first you will start with a main. Yeah, I know. Old school is that. But the advantage of this is that I can click on it and get it running. That's how a Vert.x application works. It can be embedded in a Spring Boot application and so on, but it doesn't need to be. Then you deploy a vertical, and this vertical is describing is REST API like that, using a router. So basically you say which route under what. And so the database initialization is doing the creating and stuff like that and so on. And when it's done, I'm starting the HTTP server, and then I have the 2 methods we have seen in the slides, add and list. But this was the first step. If we switch to the 4th step, here's what we have. And it's, 113 line. I lied, I say only 113. But actually this application comes with a few funky things. So we have the concurrency pattern here, concurrent pattern here. We have get price for product, so we probably have a, where it is. Here, we have the sequential patterns here, and so on. And my application is, and this is very bad. Much better. Oh no, yeah. Thank you, IntelliJ, to remind me that my Java is outdated already. Anyway, last week, or 2 weeks ago, we released Quarkus. I don't know if you heard about that. So Quarkus is a new way to make Java cloud native, really cloud native. Because as I said, Java with threads and the previous models they have doesn't really work well. You can read a lot of things about cloud native Java, but when you deploy it in production, you realize how much memory and CPU is going to use for nothing. And that's why Go and Node are much more first-class citizens in the cloud. So with Quarkus, we have decided to do that a little bit differently. And a Vert.x application can be used in Quarkus. And actually, the reactive part of Quarkus is based on Vert.x. So this application here can be run on Quarkus. So what Quarkus will bring to you is one of the features we have is to build a native image. So native executable. And I have built it. Already in target, yeah. And it's there. So I have a native executable of 27 megabytes, GVM included. GVM included. That means that the only thing you need in your containers is this. From your operating system, copy this, run. That's all. And if I run this, the application has started in 5 milliseconds. How long since the last time you start something different than an hello world in 5 milliseconds in Java? Yeah. And it's actually doing things because it's connecting to the database, and because the database was empty, creating the table and adding products and so on. And if I want to add products and see everything we see, so coffee, I need coffee. Coffee has been added. I didn't have to refresh because I have SockJS and so on. And everything, if I refresh here, it's an chunk request. So I'm not accumulating that on the server side. I'm writing as soon as I have a product coming back from the database, I'm returning this. So remember, it was 5 seconds. That's what we 5 milliseconds. Okay. Let's start with the Java version. Oops. Sure now. Same application, half a sec. 10 times. So, I have a very bad news for you, Java developer. You are back on work for at least 20 more years. No retirement for you. Sorry. And in France, retirement is a big thing, so I'm very sad. Anyway, that concludes our presentation. So we have crossed a little bit, well, we have did a journey in the reactive landscape. We have seen what reactive means, how reactive can help you today to build better systems with reactive systems, or reactive streams and reactive programming can help you to do that. If you're interested to go deeper, we have a workshop this afternoon where you will, with your laptop, develop using Eric Java 2 and Vert.x. It's based on superheroes, and you will learn about a French superhero that I discovered, which is named Frogman. It has a super leap ability. It's pretty nice.
Frogman is cool.
Sorry?
He's cool.
Well, it's a villain, but yeah. So bring your own laptop. You don't need anything except an IDE, Maven, and Git, and you will learn a lot more about this. Thank you very much. And oh yeah,
any questions?
Although the function, I don't know how it works. I open this. So. Oh yeah. How do we decide to use reactive programming?
What are the risks?
It depends on your applications. If your application is suffering about concurrency issues and start to see more asynchronous things, don't use callbacks. Go reactive. If your application is prepared to, if your application is just 5 users per days, you don't care about that. If your application is using distributed transactions, you don't care about reactive. If your applications really need to react and provide a good user experience, because that's what we are targeting, responsiveness is user experience, then reactive is what you need to investigate. The risk behind reactive, look at me, I'm a bit crazy, so that's probably one of the impact. It is a little bit too. So now the risk behind reactive is that there is a paradigm shift, and it's not necessarily easy to do it. But once you are living on the other side of the world, you will never go back.
Yeah, for early developers, it's a bit a shock to say that, okay, I'm not doing nothing, and the events are triggering. It takes a bit time, but not that much. When they are getting their hands off of it, they can write it easily, reactive code.
The second question is great.
Yeah.
Who sent that one? Yeah, I know it's written anonymous.
Don't shame it.
Okay. So what do databases are blocking? So that's not true. The database I use in my demo is using a reactive Postgre client, and everything is reactive and non-blocking. JDBC is blocking by spec, and yes, there is nothing you can do with that. But Postgre, MySQL Server, Derby, and so on, they're already asynchronous and non-blocking. The only issue is that you still use JDBC, and that doesn't work. So then there is big debates about whether we should do a 2DBC, some pivotal, AppDAV from Oracle, or something in between. It's complicated, and I don't have the time to cover there, but yeah, I'm more on the AppDAV side on this. When should not we use RP, transactions? If you use transactions, don't use. Or RP means reactive programming, I believe. I will take the last one, I believe, because then we are out of time. How can we combine object-oriented programming and reactive programming? Come to the workshop.
Yeah.
You will learn exactly this. Oh, and the difference between Eric's Java and Reactive Spring, the framework is different, but more than 50% of the code is similar. Thank you very much.
Thank you.